Okay, good afternoon, good morning, good evening, good night, depending on when you're watching this video. We're gonna work through practice problems 2 and 3 from lecture set 13. We started these problems in class. As a reminder, we are trying to predict final exam score from midterm mark, the number of hours the students slept the night before the final, and the program that they're in. And there are 3 levels to the program variable: mathematics, philosophy, or biology. In class, we have gone through and set up our models. Notably, we use different indicator setups for the morning and the afternoon sessions, but for part A, it doesn't matter. It's just to get a feel for how you would construct a model. And again, to reiterate that the most important thing with these dummy variables is a consistent reference level across both variables. Okay, in part B, we want to interpret B0, B1, and B3. So B0, we did this in class, in the afternoon class. We didn't do this in the morning class, but it's a pretty straightforward interpretation. B0 is the y-intercept. So this is the theoretical value, or sorry, the expected value for the midterm score, given that everything else is 0. So in the context of this problem, and remember that our empirical model, which is given on slide 7, it defines x1 to be the midterm mark, x2 to be the number of hours of sleep, x3 is equal to 1 if the student is in math, and 0 if the student is in philosophy, and x4 is 1 if the student is in biology, and 0 if the student is in philosophy. So we're using philosophy as the reference level for the fitted model, which means that in the case of the y-intercept, when x1 is 0, they scored 0 on the midterm. When x2 is 0, they did not sleep the night before the test. And when x3 and x4 is 0, it means that it's a philosophy student. So B0 is the expected final exam score for a philosophy student that didn't sleep the night before the test and scored 0 on the midterm. And then the question then is it a reasonable estimate? Well, 24% on a test is a reasonable value. 0% on a midterm is also reasonable. 0 hours of sleep the night before the test, this can also happen. And then 0 for the 2 indicators just means a philosophy student. So that's clearly reasonable. So there's nothing wrong with this value. B1, I believe, is 1.04, 1.08. So again, what we have to do here is we have to fix the other quantitative variable. So we can start off by saying, given a fixed or constant number of hours of sleep the night before the test, we expect a student's final exam score to increase by 1.08% for every percentage point earned on the midterm. Right? Now notice here that I don't have to condition on the student because it doesn't matter for this model if it's a philosophy, biology, or mathematics student. Switching the indicator is only going to affect the intercept term. It doesn't do anything to the slope terms. So this interpretation of B1, which is the change in final exam grade for unit increases in midterm mark, this is consistent across all students. So it doesn't matter what program they were in. This would be different though if we had the interaction model, which we'll study in the next question. Okay, the last thing that we want to do is B3. So B3 is 0.02. And from the problem description, B3 represents the indicator that switches from philosophy to mathematics. So this is saying we expect a mathematics student to score 0.02% higher than a philosophy student. Right, so interpreting the indicators is pretty straightforward. It's basically just a you interpret the slope as a shift from one level to the other. So as we move from being a philosophy to a mathematics student, that is from the 0 to the 1 level, we expect an increase of 0.02%. So a very modest difference, which is basically just implying there isn't much of a difference between how you score on this particular test if you're in math or in philosophy, because the test is likely not a specialized or a math or a philosophy test. Okay, part C. Suppose SYY is 4,656.73, N is 55, and the adjusted R squared is 0.8652. Perform a model utility test at the 5% level. Okay, this is kind of a neat problem. Oh, sorry, the question also says to assume the assumptions are intact. So this is kind of a neat problem because solving the ANOVA table is a bit different from what we've seen so far. We can use the adjusted R squared to work out some of the values. So we're performing the utility test. So we are going to have that the 4 slopes in the model are all equal to 0 versus the alternative that at least 1 beta j is not 0, j equals 1 to 4. Okay. You could also write this again as the model is useful versus the alternative that the model is not useful. We are going to run this test at the 5% significance level. Okay, and now what we have to do is find our F statistic. So this is the unique part. So we have the regression source, the error source, and the total, degree of freedom, sum of square, mean square, F. So something like this. Okay, we are given SYY. This is exactly the same thing as the SS total. So this is the 4,656.73. We are also given the sample size of 55. So that means our degrees of freedom total is 54. Okay, now we can also work out from this the mean squared total. We're going to need this to find the other values in the table. So the mean squared total, which is the sum of squared total divided by the degree of freedom total. So that is 4,000. So 4,656.73 over 54 is 86.23574. So that's this value here. Okay. Now, we know from the problem that the adjusted R squared is 0.8652. So this means that 0.8652 is 1 minus the MSE over the MST. Okay, so that means that the MSE over the MST is equal to 1 minus 0.8652, which means the MSE is equal to 1 minus 0.8652 multiplied by the MST, which is 86.23574. So if we do that calculation, we have 1 minus the R squared times MST. This gives us the MSE, which is 11.23574. 0.6248. All right, so to get that value, I've just rearranged the adjusted R-square formula. Okay, now the degree of freedom for the regression, this is easy to work out. It's just the number of slopes in the model. That's 4, which means that the error degree of freedom is 50. So now we can easily get the sum of squares error. That's going to be 11.62458 multiplied by 50. So now I'm just reversing the mean square rule. So doing that, I have 581.2289. Okay. And then the SS regression is going to be the difference between 4,656.73 and the 581.2289 that we just computed. So that gives me 4,075.501. And then my mean square regression is going to be 4,075.501 over 4, which is 1,118.875. And that gives an F statistic of 87.64837, where the F statistic is just found by taking the mean square regression over the mean square error. Okay, so this is our ANOVA table, and now we have the test statistic. Notably, I skipped writing down some of the calculations, but a lot of these we've seen many times so far. The addition or the additive property of the degree of freedom and the sum of squares, I utilized that. The multiplicative or divisive properties to get the mean squares from the sum of squares, and then the F statistic being the ratio of the two mean squares. These are all things that we've seen numerous times throughout the ANOVA studies, and then again in the regression case. So I wrote down the rules that we wouldn't have seen as often. For example, the mean square total rule. This is the same mean square rule for the other values. And then the manipulation of the adjusted R squared. That's something that we haven't seen explicitly. So I used or showed how I worked that value out as well. But from this point, we can now take the approach that we usually take. So for example, if we take a critical value approach, here's my F curve. So I'm going to have an F on 450, 0.05. Okay, so I need to pull out my tables here. Yeah, this is going to be as close as we can get. So we have 4. We round down to 30, 0.05. So that gives us 2.69. So we're going to use 2.69 as the critical for this test. And then notably for the p-value part, you can see the highest value in this slot is 4.62. Our p-value is very, very big. So we're going to be able to, we can kind of determine already what the p-value is going to be based off the size of that statistic. Nonetheless, so here we're going to say use F for 30, 0.05, which is 2.69. Let's confirm that. Right, and then we can see that our test statistic is well inside this region. Right, so we'll be able to reject. And then if we take the p-value approach, well, it's a better F curve on the second try. All right, so this is going to be a very small value, but strictly speaking, we would have a p-value, which is the probability in this case that an F exceeds 87.648. Okay, and then we could say from the table, I'll go back and show this in a second, but given the size of this, we're only going to be able to take the smallest option. Okay, so our p-value is going to be less than 0.005. And this is true because if we go back to our section of interest, which is at 4 and 30 here, we're going to be working in these blocks of numbers. We can see that our test statistic is here, right? So that's 87.6. So we are bigger than the biggest value, which means that we must be smaller than the smallest listed value given here, right? But in this case, you could also write the p-value is approximately 0. That would be equally acceptable in this problem, right? So we have overwhelming evidence in this case, so we can reject H0. And then we can write at the 5% significance level, the data provide sufficient evidence to suggest that the model is useful. All right. Okay, number 3. So number 3, it's the exact same situation. We've added in 2 indicators. So we're mixing the midterm mark with the 2 categorical variables now. So the first thing that we're asked to do is interpret B5. So B5 is 0.24. Okay, so in this situation, when you're mixing or when you interact a categorical variable and a quantitative variable, you actually do have a direct interpretation of what that slope is. This is different from when you interact 2 quantitative variables. Interpreting the double quantitative interaction is more difficult because effectively the effect that the interaction has on the slope of that it's attached to, so in this case x1, changes every time you change the other value. But for the categorical variable, which only has 2 values, we actually can interpret what this is doing directly. So first off, let's just consider 2 things. When x3 is 0, b3 goes to 0, right? So when x3 is equal to 0, this term cancels out, so it doesn't have any effect. When x3 is equal to 1, b3 is equal to 0.24 in the model. So what this is showing us is this term is only active when you're in the active level, which is the mathematics student. So when x3 is equal to 1, we have a mathematics student. So this slope term only applies to mathematicians, and we can compare it to the reference level, which is philosophy. Now, what this term does is it directly changes the slope of x1. So what we can say here is we expect a mathematics student to score 0.24% higher than a philosophy student for every additional percent earned on the midterm, right? So it's sort of the interaction between the quantitative and the qualitative variable is sort of a hybrid between interpreting the slope of that value and just interpreting the qualitative variable directly. So we still have a transition. We're moving from philosophy to mathematics student. So we have that switch across levels. But now what the interaction represents is the change in the slope. So if we have a philosophy student, which means that x3 is equal to 0, x1 stays at 1.08. So for every gained on the midterm, a philosophy student will earn 1.08% on the final. But when we have a mathematics student, the interaction turns on. So 0.24 gets added to 1.08. And now what we would be saying is for the mathematics student, we would expect their grade to increase by 1.08 plus 0.24% for every percent earned on the midterm. But the direct effect, the interpretation is in terms of the difference, which is the 0.24. So what we can say is between a philosophy and a mathematics student, every time each student earns a point on the midterm, their score on the final is going to change at a different rate. So the philosophy student's score in the final will consistently move up at 1.08. The mathematics student's score on the final will move up at 1.08 plus 1.24 or plus 0.24, so 1.32. But the difference is that 0.2. So at every point, there's 0.24 values apart on their final exam score. And that's what we're reflecting here. Okay, in part B, we're going to do a model or a extra sum of square F test. So it says test if the interaction terms are required at the 5% significance level if the SSE of the larger model is 7.3426. Okay, so first off, we have two models here. The reduced model is the first model from part 1. So this is the model without interaction terms. And then the full model is the model in question 3, which is the MLR model with the two interaction terms. All right. So we want to run an extra sum of square F test to see if these two interaction terms are useful. And remember, this was one of the points that I was raising in lecture, that the extra sum of square F test, it can be used to compare any subset model to any full model. So it doesn't only have to be one term different between the two models. It can be multiple terms that are different as long as the reduced model exists inside the full model. So here we're actually testing two interaction terms at the same time rather than just one. So the null is that the reduced model is adequate, and the alternative is that the full model is required. Okay, and then we're going to test this at the 5% level. All right, so on step 3, the formula for our extra sum of squares F test is the SSE of the reduced model minus the SSE of the full model divided by the degree of freedom error for the reduced model minus the degree of freedom error for the full model. And this whole thing is over the MSE of the full model, which is on the formula sheet is written as the SSE full over DFE full, but that is the mean squared error by definition. Okay, so the SSE for the reduced model, we worked this out in problem 2. So this is 581.2289. And then the SSE for the full model is given to us in the problem description. It is 7.3426. Okay, and now we're going to divide by the degree of freedom error for the reduced, which we worked out to be 50. And then the degree of freedom error for the full has 2 more regression terms than the reduced model. So that means that its error regression is going to be 48. The other way you can think about this is the degree of freedom total doesn't change. It stays at n-1. So it's always 54. We have two additional regression terms in the model. So the degree of freedom regression goes from 4 to 6. 54 minus 6 is 48. And then on the bottom, we have the SSE full divided by its degree of freedom. And if we do this calculation, we get, or at least what I got, and hopefully is correct, is 24.68418. Okay, more testing. So if we take the critical value approach, all right, so we have an F on 250, 0.05. So you'll notice that I'm just taking the degree of freedom in the numerator of the F statistic and the degree of freedom calculation in the denominator of the F statistic. So the 2 is 50 minus 48, and the 50 is 50. So we go back to our F table now. We know we're going to have to use something in the 30 slot. We're going to be in the second column because we have 2. So we're at 230, 0.05, which is 3.32. Okay, so we're going to use F to 30, 0.05, which is 3.32. And then we can see that our test statistic again is well inside the region. And then if we take the p-value approach, all right, so we can mark down our test statistic. We can shade this region here. So we have that the p-value is the probability that F is greater than 24.684. We go back to our table, same result that we had in the last problem. So we're in this section. Our test statistic is going to be located here above the highest listed value. So if we're greater than the largest number in the column, we're less than 0.005. So again, we can say therefore the p-value is less than 0.005. All right. Oh. So once again, we would reject the null. And on step 6, we would say at the 5% significance level, the data provide sufficient evidence to suggest that the full model is required. Okay, part C asks for us to compute the adjusted R squared for the larger model, for the full model, and then if it supports the conclusion in B. So we're going to have R squared adjusted is 1 minus MSE over the MST. This is going to be 1 minus 7.3426 over 48. So I'm using SSE divided by SSE divided by DFE to get the MSE. The MST will be the same value from the reduced model. This doesn't change. So the sum of square total and the total degree of freedom don't change. So the MST will be as we found it in the ANOVA table, 86.23574. All right, and then this gives us 0.9982. And then we can say here, since RA squared for full is much larger than RA squared for reduced model, the RA squared values support the conclusion in B. Right? Because B said there's statistical evidence that we need the full model. The adjusted R squared is implying that the full model is a significantly better fit. You go from explaining approximately 87% of the variation in the data to explaining effectively all of the variation in the data with the interaction terms. So given that the interaction terms in this case are actually pretty easy to interpret because we're mixing a quantitative and categorical variable, the R squared is almost is roughly 13 points higher than the R squared for the full model is roughly 13 points higher than the R squared for the reduced model. And the result of the extra sum of square F test, it seems like the full model is a better fit. All right, so that's it. See you guys in the exam.